Okay, I'm recording. Here we go. Welcome back, lecture 4. Today I am going to keep it short. It'll be the lecture and that'll be it. So we've seen up to now, we've looked at we've reviewed the decimal system. We've introduced the binary system, and we've seen how to convert from one to the other, and we've seen some basic operations, including subtraction and complements, right? Okay. Today, I am going to redo basically the same. It's just the same basic principles, but in two different bases, base 8 and base 16, which are fundamental for computer scientists and computer science. And I'll try to explain a little bit why that is. Now, in the book, this is in chapter 2, which is entitled Computer Codes. Let's forget about that for now. We'll start that properly next week. So now you can just think of octal and hex simply as an extension of what we were doing up to this point, okay? So let's start with octal, which is close to, it's very, very close to decimal. It can get confusing. You have to be very careful. The numbers just look like you're looking at decimal numbers, right? But it's base 8, okay? So one of the reasons that this is so important for us is, and I'll get back to that a little later, is that this is like binary for humans. Basically, it's readable binary, right? So binary for humans, in a sense. We'll see that one octal digit is the equivalent of 3 bits. Okay, I'll get back to that. So one octal digit encodes exactly 3 bits. That's the key point, if you wish, in for octal. Okay. All right. So let's just review the basics here. So this is base 8. Of course, it's the same positional system, right? So we'll have to look at some basic powers of 8, which is our base. 8 power 0, of course, is 1. 8 power 1 is 8. And this grows pretty quickly. And unfortunately, it's not 10, right? So we're used to 10, so we can write those down very easily. But if you want to write the powers of 8 in decimal, then this is not so easy. So 8 squared is 64, 8 cubed, and I'm cheating, I'm reading them off my sheet here. And you see these get big quick. Okay. So oh, by the way, I'm not going to do fractions. I'm just going to do sum and difference. We're not going to multiply an octal. It's sort of pointless to do that. So let's take a look at what I mean by the positional system here. Let's do an example. So if I write 1, 0, 2, 5 in octal, which I'll indicate by putting an index 8, okay, so this is written in octal, so this means the following. So this is 1 times 8 to the power, so 0, 1, 2, 3, 8 power 3, plus 0 times 8 power 2, plus 2 times 8 power 1, plus 5 times 8 power 0, right? So rather than base 2 or base 10, it's base 8, so it's exactly the same principle. So if you want it in decimal, this is how you expand it. So in this particular case, this would be 512 plus 0 plus 16 plus 5, which turns out to be 533. This is in decimal, right? Okay, so this is how you read off, a number in hex, okay? So this is how you go from sorry, in hex, in octal. So you go from octal to decimal, you just read it off, okay? There you go. Okay, how do you then convert the other way around? Well, okay, so conversion decimal to octal. Okay, so how does this go? Well, if you think back how we did for binary, what we did was successive divisions by 2, which was our base. So this will be successive divisions by 8. The base, right? So for any base, this is the trick. This is always the same thing, okay? So here is a simple example, just to illustrate. Let's say that I'm asked to convert 234 to octal. So I want to write it down in octal. So I just successively divide 234 by 8. So let's do it. Okay, so 8 times 3 is 24. So that's 2 times 8. That's 16. That's 7. Bring down the 4. 9. That would be 72. Hopefully I'm right. And that leaves 2. Okay, so what's the next step? You take your 29, right? This is your remainder, 2. Okay, so then you repeat with 29, divide by 8. You see that you'll have less divisions to do than by 2, right? If you have divisions by 2, the divisions are easy, but you have tons of them. If you're dividing by 8, divisions are a bit longer, but you have much less to do. Okay, so this is 3 times 8 is 24, leaves 5, right? That's a remainder. Then repeat. Always be careful with the last steps. 3 divided by 8, this goes 0 times, leaves 3. This is your stop sign, right? So you have your remainders, and in which order do you read them? You have to remember that you read them this way, right? So 2, 3, 4 in octal is 3, 5, 2. Okay, and you can check. You should check if you're asked to do this, right? So how do you check? Well, you expand the octal, right? 3 times 8 power 2 plus 5 times 8 power 1 plus 2 times 8 power 0, and you should get 234. Okay, so basically there's really nothing new here except that we're using 8 as our base rather than 2 or rather than 10. Okay, all right. Let's now look at the first few integers in octal and in binary, okay? Just to compare. So first, integers in binary and octal. Okay, so here are the octal digits. The first, well, octal, not just the digits, but so 0, 1, 2, 3, 4, 5, 6, 7. What is 8 in octal? 1, 0, right? So that's the next number in octal, and you keep on going. Let's look at them in binary now. Okay, and I'll write them on 3 bits. Well, actually, I might need a little bit more, but let's just, okay, I'll write them on. Okay, so up to this point, I'll use 3 bits. Okay, so binary 0 is 0, just 0, 0, 0. 1, what is 2 in binary? This is 1, 0, right? 3 and 4 and 5 and 6 and 7, right? And then you need an extra bit. Once you go to 8, obviously you need the extra bit like that. But if you look at just the octal digits, you see that it corresponds to precisely those numbers you can write in binary on 3 bits. So all numbers that require exactly, or at most 3 bits, I should say, right, in binary. Why is that? Well, 8 is 2 power 3. That's because 8 is exactly 2 power 3, right? And so that means, if you look at just this table, that if you're looking at a single octal digit, it corresponds to exactly 3 bits, okay? So the moral of the story, so 1 octal digit is equal to 3 bits, okay? So what does it mean for conversions between octal and binary? It means like it's super easy, okay? So that's the moral of the story. Because 8 is a power of 2, 10 is not. That's why it doesn't work very well from base 10 to base 2. I mean, it's not hard, but it's not natural in a sense. But if you go from, hello, if you go from base 8 to base 2 and back and forth, the conversions are easy. So octal to binary conversions, this is super easy. Okay, so let's just illustrate this. Okay, so here's an example. So convert 4206 octal to binary. Okay, so what do? I just look at each octal digit and write it on 3 bits, and that's it. Okay, so let's look at 6. What is 6 in binary on 3 bits? That's 110, right? 4 plus 2 plus 0. What is 0? It is 000. What is 2? 010. And what is 4100? Is that okay for everybody? Does that make sense?
Yes.
Yes. All right. Good. Great. Thanks. Okay. So I'm converting each digit or octal digit to 3 bits. And so what is the resulting binary number? It is 100,010,000,110. So this is our answer. That's it. That's as simple as that. So you see from this exactly, because you see each octal digit encodes exactly 3 bits. And when you're multiplying by 8, you're shifting by 8. So in binary, you're shifting by 3, right? That's 3 bits each time. So octal is basically like a compact version of binary that's easily readable for humans, right? That's what octal is, okay? What about the other direction? What about binary to octal? It's the same thing, right? So let's say that I'm asked to convert 101101101010 to octal. Okay, now here you have to be careful. You always start on the right. You're going to group everything from the right, not from the left, right? So just the only caveat here. So group starting right right? This is important. Okay, so I'm looking at groups of 3 bits. Now, you see here that I don't have 3 bits at the beginning. That's fine. You can just pad if you wish, if you prefer. Okay, so so what is this? This is 0, 0, 1, 0, 1, 1, 0, 1, 1, 0, 1, 0, 1, 0, 0. These are my groups of 3 bits, and I just rewrite them as an octal digit. So this is 1, this is 3, this is 3, this is 2, and this is 4. And so my number in octal is this. And that's it. Okay? So binary, so this is the simplest way to convert to yes. Binary to octal, octal to binary is just, you're just grouping the bits and that's it. That's super easy. Man, I've got to find a way to, okay. All right. Okay, so octal binary, binary octal, like super straightforward. It's just 3 bits at a time, okay? All right, so now let's take a look at arithmetic in octal. And again, I'm not going to do division. We didn't do it in binary. We're not going to do it in octal for sure. And we're not going to do multiplication either, okay? There's really no point. And I'm not going to do fractions either. I mean, we could do it, but we're not going, it's not, conceptually, there's nothing new and it's not useful. So there's no point, okay? So we're going to do sum and we're going to do subtraction. And subtraction, we're going to do it using complements. That's the simplest way. Or a more interesting way, whichever way you prefer to see this. Okay, so let's start with the sum of octal digits. From a technical point of view, if you're doing this by hand, which in theory you'd have to do, what I recommend is, so we're decimal beings. We've been trained in decimal, so this doesn't come easily. So what I suggest to do is write it down in decimal and then convert to octal. So what I mean is this, okay? So write it in decimal first. Okay, so what I mean by this is this. So when you're adding, it's just a normal way of adding, but let's say that you have the digits 5 and 4. Everything here is an octal, right? So 5 and 4 is 9, which is not an octal digit, right? So, but in decimal, it's 9. I'll write it in decimal, right? So what is that? That's 8 plus 1, right? So this is 1 and a carry of 1 in octal, right? Here's another example. Let's say that I have 6 plus 7. So these are octal digits that I'm adding in some big sum that I'm doing. 6 and 7 is 13. I'm going to write it in decimal first, right? Now, 13 decimal is 8 plus 5, right? So this is 5, and you'll have a carry of 1. So in octal, and so on and so forth, okay? Or if the digits are small, then of course it makes no difference. So if you had 3 plus 4, that would be 7 decimal, but that's the same as 7 octal, right? It's the same thing. Okay, so let's see how this works when we have bigger numbers. So for sum in general, so use the above method and carries, obviously. Okay, So here's an example. I'm asked to add, to compute the following. Sum 7346 octal plus 5263 octal. Okay, so it's just a normal sum. Okay, so I'll just the same method as in decimal or binary. So I just put these numbers one on top of another. But I'm going to do this extra step that I'm going to write down in decimal. I mean, if you're like super smart, good, whatever, you can try to go faster and just not write the decimal part. I don't recommend doing that, but I mean, it's up to you, obviously. But let's say that I do this intermediate step here in decimal. So 6 and 3 is 9 decimal. This is 8 plus 1. So this is 1 and a carry of 1, right, in octal. 6 and 4, 10, 11. So that's 11 decimal, which is 8 plus 3, right? So this is a 3 and a carry of 1, right? 3, 2, and 1 is 6, which is just 6 in octal. 7 and 5 is 12 decimal, which is 8 plus 4. So that's 4 and a carry of 1. Okay? So I have this intermediate decimal step, which makes it easier for me to write down. So the answer here is 7346 octal plus 5263 octal is equal to 14631 octal. Okay, hopefully that makes sense. All right, so it's the same thing in any base. Okay, it's just that if we have to do it by hand, sometimes we need these little tricks not to mess up. For example, when I mentioned that when you're multiplying in binary, you should keep a running sum rather than try to add a whole bunch of binary numbers together. If you're doing this by hand, it's a mess. Okay. Okay. Hopefully this is okay. So let's move on to the difference now. Okay. So octal difference. We're going to use complements. Okay. So how did this work in binary and in decimal? You remember in decimal we had the nines complement where you do 9 minus each digit. The tens complement, you add 1 to this. In binary, you had the ones complement, which you just flip the bits. The twos complement, you add 1. So what is it in octal? You'll have the sevens complement. So this is 7 minus each octal digit, right? And the eights complement, this is the sevens complement, and you add 1. Okay. And how do you subtract? If you have A, B numbers with the same number of octal digits, right? So this is always important. If they don't have the same number of digits, you have to pad, okay? Then B minus A will be B plus the eighths complement of A and remove the leading 1. You always get a 1 in front. Same in any base, okay? Okay, so here's an example. So this is very efficient. This is very easy. 7526 octal minus 3142 octal. I want to compute this, okay? So I'm going to compute the 8's complement of 3142. So the 7's complement, let's start with that. So what do I do? It's 7 minus each digit. So this is 4, 6, 3, 5, right? The 8's complement, I just add 1. So that's 4, 6, 3, 6. And then I add 7, 5, 2, 6, 4, 6, 3, 6. Again, careful, these are octal. I'll do a intermediate step in decimal here. So this is 12, which is 8 plus 4. That's 4 and a carry of 1. 3, 2, and 1, that's 6, which is 6. 6 and 5 is 11, which is 3 and a carry of 1. That's 12, which is 4 and a carry of 1. But I'm doing a subtraction using the complement, so the leading one is removed. Right? And so the answer is 4364 octal. Okay. I know I am not doing this very slowly. I'm going through it, but hopefully if you remember, practiced a little bit the binary method, it's exactly the same thing, except it's base 8. Okay. So this is the same trick. So again, make sure you have the same number of digits. Otherwise, this is going to mess up. So pad otherwise. And just add the 8's complement, remove the leading one. That's it. Okay. Any questions at this point? Comments? We are very fortunate because there's like construction right
I have a
outside.
question.
Yep.
Do we also remove it when we sum it up? When
Do
we
we
add,
also?
like, if do we also have to like match the same number of digits when we add up?
Sorry. Give me some is your question the following? Should we remove a leading one when we're just adding numbers? Is that your question? Or not?
Yeah, if there's like an extra one, like in this situation.
Okay, so let me go back to my example of, okay, so let's look at this example. I had a sum. In this case, if I understood your question correctly, okay, here I do not remove the leading one because, I mean, I'm actually doing a sum, right?
Okay. Yeah.
So here I have to keep it. If I remove that leading one, I'm not going to get the right answer, okay? But if I'm subtracting, then the trick with the complement adds this extra one, which is not there. We, in the algorithm to compute the difference, this has to be removed.
Okay, I understand. Thanks.
Yeah. Okay. Good. All right. Okay. So that's octal, and now what I'm going to do is do exactly the same thing, but this time in base 16 hexadecimal. So there is a slight, just a slight technical difference, and you'll see, I mean, you may have heard, you might all be familiar with hex, but or not, it makes no difference. So this is base 16. Notice 16 is 2 power 4, right? So again, this should work well with binary. So it's the same principle as octal, okay? It's even more compact than octal, right? So your digits have more information in each one of them, right? This was first developed in the 60s at IBM. This is the version we're using today. Okay, so this is the current version. There was an older version that was developed in the 50s, but they didn't use quite the same symbols. Okay, original version is from the 1950s. Okay, it's slightly different. This is used everywhere. It's used in C++, Java, HTML. And again, this is basically just an encoding of 4 bits at a time. Okay, so this is binary for humans. So each hex digit, hexadecimal, it's long to say, so we say hex. Each hex digit encodes, this time, 4 bits, right? 2 power 4. Okay. Okay, so now you see that we're going to run into a problem here because we have more digits than base 10. Okay, so so again, this is a positional system. Positional system. Base 16. So we need 16 digits. These are the hex digits. Okay, but in decimal we have less, so we need to introduce some new digits here. So what are they? Well, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and then the convention is we use capital A, capital B, capital C, capital D, capital E, and capital F. Okay, so these are in decimal, right? So in decimal, these are 10, 11, 12, 13, 14, and 15. Okay, so we have a single symbol that's worth 12. That symbol is C, right? So we need a digit for each number between 0 and 15. So the convention is we use capital A, B, C, D, E, F. Okay, so again, it's a positional system with base 16. So here's an example. How do you read this off? So if I write A9C4 in hex, what does it mean? This is equal to, so 0, 1, 2, 3. So this is 10. A is 10, right? Times 16 power 3 plus 9 times 16 squared plus C is 12. 12 times 16 power 1 plus 4 times 16 power 0. So then this is compact, right? Numbers get really big in decimal, much bigger than in hex because the base is bigger. So if you add that all up, you will get 43460. This is in decimal. Okay, so it's a bit more compact than decimal. Okay. So how do you convert from hex to decimal? That's the way, right? You read it off, right? How do you convert from decimal to hex? So if you have a decimal number and you want to write it in hex, what do? Yeah, you grab a calculator, but no. So the question is, what does the calculator actually do? Okay. In the end, what it does is successive divisions by 16, right? That's what happens. So successive divisions by 16. Okay. Now, I'm going to do an example in just a sec, but well, yeah, I might as well. Okay, let's do it. Why not? I have one here. Yeah. Okay. Here we go. So let's convert 9719. That's in decimal to hex. Okay, so I want to do that. So I'm going to do successive divisions by 16. So 9719 divided by 16. 6 times 16 is 96. Okay, so that's 1. Bring down a 1. How many times does 16 go into 11? It doesn't go at all, so that's 0. Bring down the 9. 119, I'm going to cheat here. I'm just going to look at my notes because otherwise it's going to take forever. 16 times 7 is 112. So that'll leave a remainder of 7. Okay, then what do? I repeat. Oh yeah. 607 divided by 16. 4 times is 64, so that'll be 3 times, which is 48. That leaves 12. Bring down the 7. 8, 9, 7. It's 7. Is it 7? 112, 16. Yes, it's 7. It's the same as the previous one. So 7 times 16 is 112. So what did you do today? I watched some guy divide numbers by 16 on TV. It was real fun. So this is 15. That's my remainder of 15. And I repeat, we're almost there. 37 divided by 16. 2 times 16 is 32. That leaves 5. And then 2 divided by 16 goes 0 times. That leaves 2, and I stop. Ooh, okay, not so bad, not so bad. So how do I read it? Usual way, you read it off this way, okay? So this is, so 9719 decimal in hex is 2, 5, no, the other way around, sorry. 2, 5. What is 15? I need a digit. You can't write 15, right? It's, yeah, F, right? And 7. So this is the number in hex. Did I? No, sorry. I did a double switch here. I'm sorry. This is completely wrong. I was right at the start. So I'm reading it this way, but left to right. So 2, 5, F, 7. Sorry about that. Okay. Yes. So the first number that you get, right, is always the least important digit. It's the rightmost digit, right? Okay. So this is 9719 in hex. All right. Okay. So again, it's always the same thing. Now, about conversions to binary, this is nice. This is super nice. Okay. So hex to binary and vice versa conversions. This is easy, right? So the trick again, so let's write down the first hex digits. 0, 1, 2, 3, 4, 5, 6, 7. Let's write down the first few numbers in binary on 4 bits. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Oops, not 10 like that. I want to write it in hex. 10, 11, 12, 13, 14, 15. So 8 is in binary is 1000. Then I keep on going, 1001, 1010, 1011, 1100, 1101, 1110, 1111. Sorry, it's a bit difficult to line up. But you see that the 16 hex digits correspond exactly to everything you can write down on 4 bits. Okay, so that's the trick. Just like in octal, but rather than 3 bits, it's 4 bits. Okay, so here is an example. Let's say I want to convert A7B. This is in hex to binary. So what do? You take each one of the digits and you write it on 4 bits. Okay, so B is 1011. 7 is 0111. 8 is 10. This is 1010. This is 1010. And so the resulting number, I'll leave spaces in, it's easier to read, but this is how you get from hex to binary. Okay, it's just 4 bits at a time. That's it. Okay, and if you want to go from binary to hex, you chop it up into pieces of length 4, starting on the right. This is important. Okay, so let me do one here. Okay, so convert 1 okay, to hex. Okay, so suppose I do that, then so group into 4 bits starting on the right. Okay, this is important. So let's just, let's do this. Okay, so I've got this. I'm going to split them up into 4 bits like that. Man, I have groups of, that's what I didn't want. I'm going to change the example. Okay, sorry about that. Let's put a 1 0 in front here. Okay, that's what I wanted. Okay, so you chop it up into 4 bits starting on the right. Okay, if you don't have enough bits at the beginning, that's not a problem. But you see that if you start on the left, it mess everything up. It has to be starting on the right. This is important. Okay, 1011. That's 8. That's 11, right, in decimal. So that's B. This is 1. That's 13. That's D, right? If I mess up, tell me. I sometimes I'll mess up D, C, E. You have to be careful. 1011. That should be B again. 1011. That's exciting. Okay, and 10. If you can add those 2 zeros at the front if you wish. I can put them there, right? But that's 2, right? So this is the number in hex. So 2B, B, D, 1B, X. Okay. Hopefully that's okay. Okay. And finally, for hex, sum and subtraction, same principle as the previous bases. Okay, so arithmetic in hex. Again, we're not going to do fractions, but you can guess how this would work, right? I'm not going to do division. We're just going to do we're not going to do multiplication, just sum and subtraction. And again, subtraction will be using complements. Okay, and again, if you're doing it by hand, then I strongly suggest that you write it down in decimal before you. Okay, so here are some examples. If you're adding hex digits, and you might even have to subtract writing it down because now the numbers are getting pretty big. Okay, so here's an example. So let's say you're adding two hex numbers, and at some point you get the sum a plus 7. These are two digits, so that's 10 plus 7. So in decimal, that'll be 17, right? Which is 16 plus 1. I'll subtract the 16, right? 1, like this, and a carry of 1, right? Because of the 16 that you're removing, that's your carry, right? So, and carry of 1, okay? So in other words, 17 in hex. So in other words, 17 is 1 hex, right? So it's 16 plus 1. Okay, here's another one. Let's say I have C plus D when I'm doing a sum of two numbers in hex. So what is that? So C is 12, right? D is 13. So it'll be 25 in decimal, right? And I want to write this whole thing in hex. So I remove 16. So that will leave 9, right? And so I'll have a carry of 1, right? So in other words, what I'm saying is that 25 is 19 in hex, right? It's 16 plus 9, that's 25. Okay. All right. So let's do one. Let's do a big number. Again, if you have questions, anything, just interrupt me by using your voice, your hand, your chat, whichever is more convenient for you. Okay, so here's an example. Let's compute the following sum. C868 plus 72D9. Okay, so it's the same principle always, except technically we have to be careful here because numbers are a little bigger. So okay, so I'm going to do this extra step here, or extra steps if you wish, but 8 and 9 is 17. That's decimal, right? If I remove 16, I'll get 1 and a carry of 1, right? So minus 16. I can do that. So 1 carry of 1 because I've removed the 16. Okay. D is 13. 13 and 6 is 19, so that's 20 decimal. I remove 16. I get a 4, and I get a carry of 1. Okay. 8, 9, 10, 11 11 decimal, there's no 16, so it's just a digit. So that's B in hex, no carry. C is 12. 12 and 7 is 19. If I remove 16, I get a 3 and a carry of 1. So 1, 3, B, 4, 1 in hex. So this is 1, 3, B, 4, 1 in hex. Okay? So again, it's always the same principle. Okay? All right. So finally, last thing I want to do today is subtraction using complements. So our base is 16. Let's just switch that. So subtraction. If I have a number in hex, the base is 16. So now the complements will be the 15's complement. That's how it's called. How do you do that? It's 15 minus each digit. Okay, that's the recipe. What's the 16's complement? Same thing. It's the 15's complement, and you add 1. Right? And how do you subtract if A and B have the same number of hex digits? What do you do to compute B minus A? It's the same thing. B minus A will be B plus the 16's complement of A, and then remove. You're going to get a leading 1, which is not supposed to be there. Remove a leading 1. Okay, so it's always the same, exactly the same recipe. I can do an example, and that'll be it. Let's do that. Okay. I don't know if you guys can hear the construction. It's pretty bad. Right outside my window, it should be over by the end of the week. Okay, so we're asked to compute 17284. This is in base 16 minus 4E86 in base 16. What is the first thing that you notice which is molto importante? Very important.
The two numbers aren't the same size.
Correct. They don't have the same number of digits. So you have to make them the same number of digits, right? So okay. So what do? You put a 0 in there. So it's 172. I'll drop the, we know we're in hex now, so I'll just drop the index 16. So 0, 4, E, 8, 6. This is really important, okay? Before you do the complement, because otherwise the technique does not work. Okay, so let's copy this, and I'm going to switch slides. I'm just going to copy it down here. Paste. Okay, so now the 15's complement of 0, 4, E, 8, 6 is what? So I'm going to do 15 minus each digit. So 15 minus 0 is 15. That is F. 15 minus 4 is 11. which is B. 15, so E is 14, so that'll leave 1.
16, isn't it?
Sorry?
The E, isn't
E.
it 16 instead?
Nope. A, B, C, D, E, F. That's 10, 11, 12, 13, 14, 15.
Okay, my bad.
Yeah, it's okay. Yeah, you should check me because I can mess up, and not on purpose. Okay, so then 15 minus 8 is 7, and 15 minus 6 is 9. So this is the 15's complement. If I add 1 to this, now it's so tempting to put a 0 and then do a carry of 1. It's so tempting because we're just like, our brain is, but no, that's not it. Okay, so FB17A, careful, be really careful. Okay, so this is the 16's complement, okay, of our number. So now I'm going to add 172A4 plus FB17A. Okay, so again, I'm going to do this little extra step in decimal because I'm a human being. So 10 and 4 is 14, which is E. No carry. 10 and 7, that's 17. So that's 16 plus 1. So that's 1 and a carry of 1. This is 4, which is just 4. B is 11. So this is 18. So that's 16 plus 2. So that's 2 and a carry of 1. This is 15, 16, 17, which is 1 and a carry of 1. And again, this is always gone, right? Because I'm doing a subtraction. So this extra 1 is just not part of my answer. So the answer will be 1241E. This is what I'm looking for. Okay. So again, if they don't have the same number of digits, pad. So then you can take the complement. And when you're doing a subtraction using complements, if you don't get a leading one, you know something is wrong. Either you didn't have the same number of digits, or you subtracted a small minus a big number, which you shouldn't do, or you made some arithmetic mistake. Okay, so when you're doing a subtraction using complements, you will always get that leading one that you have to remove, always. Okay. Okay, so this is it for Octal and Hex. I will set up a new WebWorks. Don't forget, you have a WebWorks right now on arithmetic. It's due Monday. I'm going to set you up with a new one with Hex and Octal. And just don't forget to do them. These are like points in the bank, marks in the bank, right?
Sir, I have a question.
Yep.
Yeah, when's gonna be the first quiz?
There are no quizzes.
No?
Do you mean test?
Yeah.
Early October. I will tell you soon the precise date.
All right, cool.
Okay. Yeah. Yeah. First test will be early October. Yeah. Other questions? Nope. Okay. So that's it for today. And have a good weekend. And I'll see you on Monday.
Thank you,
All
sir.
right, take care, sir.
See
Bye,
you.
sir. Thank you.
See you.
Take care. Thank
Bye,
you.
sir.
Bye-bye.
Sorry, I'm not gonna lie. I kind of fell asleep for like a little 5 minutes.
So, what?
I said I'm not gonna lie. I fell asleep for a little 5 minutes. I'm
Oh.
sorry.
Okay, all right.
Oh
So
God.
you've just been recorded saying